Hello student to the Foundation of Classical Electrodynamics course. So, we are in module 3 now, and module 3 under lecture 55 we will going to discuss more about the magnetic vector potential. So, the discussion will be continued today. So, we have class number 55. So, our discussion on magnetic vector potential will continue. So, in the last class we calculated the magnetic vector potential for few cases. So, today we will going to do another thing, and that is vector potential. Try to find out the vector potential for a constant magnetic field. So, a magnetic field that is given is constant, and corresponding to that magnetic field, if I want to find out the vector potential, so what should be the form of that we consider. So, let us consider a uniform magnetic field. So, uniform magnetic field is there B0, and we considered that this B is along the z direction. So, if this is my coordinate system x, y and z, so B is along this direction, it is uniform. So, we have B0 z unit vector. So, that means B0 vector is magnitude B0 with z unit vector, it is in this direction. Now, I need to find out the A. So, let us exploit this expression that curl of A is B, and so that means the ith component of the B is simply epsilon I j k del j a k. So, if I want to find out the x component B x, it should be del y a z minus del z a y, and that is 0. If I calculate the y component of the B, that is del z a x minus del x a z, that component is also 0, and the B z component is del x a y minus del y a x, and that component is non-zero, and this value is B0. Okay, so, I have 3 equation in my hand, 3 partial differential equation in terms of A. So, one possible solution, so one possible solution is this. Let us consider A x to be 0 with A z to be 0. So, A x A z 0 and A y is equal to x b0. If I put it, you can see that it will going to satisfy, because az is 0, ax is 0. So, then ay is ay is x b0. So, the first equation will going to satisfy, second equation will going to satisfy, and third equation is also going to satisfy, because ay is x b0. So, when you make a derivative here, so you will get b0 here and rest of the term will 0. So, all the three equations will going to satisfy. The similarly, or I can also construct the solution in this way, say ay and az is 0 and ax is minus of y b0. You can check it that this equation, this solution can also satisfy these three equations what is given here. Now, if two solutions are there, the linear combination of these two solutions is also a possible solution, and if you do that, then I can have another solution. So, the possible linear combination, so the linear combination of this solution, if I make, then I can have say a solution like ax is equal to minus of half y b0 and ay is equal to half x b0 and az is equal to 0. The linear combination of these two equations leads to. Now, in this case, a can simply be written as, these components are there. So, a can simply written as half b0 cross r. This is the way you can write, and now if I make a curl of both the side, then you will see that it is satisfying, it is giving you the constant value b0 as a magnetic field. So, ai is simply half epsilon I j k b0 j and r k. So, after that, so this is my expression, right. This is my expression for constant magnetic field. I can always write A in this way. So, this is one of the solutions for constant magnetic field that I can use. Now, if I now check carefully, so this is so B is along z direction, right, according to this figure. So, let me write down this let me draw this figure once again. So, I have the coordinate system like this. This is x, this is y, and this is z. This is z, and if I make a circle here, and my B is along this direction, which is B0 z unit vector. R is this one. This is my R, right. Now, what is the direction of A then? This is B0 cross R. So, it has to be in a tangential direction, like this. So, this is the tangential direction. So, this should be the direction of vector A, right. So, every time r changes, so this direction will going to change. Now, if I integrate, so if I integrate, so over this circle as a closed line integral, if I calculate this quantity A dot dl, then what I get? This quantity is simply the surface integral cross curl of A dot ds, and curl of A is nothing but B. So, surface integral B dot ds, and B dot ds is nothing but the magnetic flux. This is simply the magnetic flux. This is simply the magnetic flux. So, B is along the z direction, and we can have the magnetic flux here, and this magnetic flux can be calculated by this expression, that if A is known, then from that, exploiting that A, one can calculate the magnetic flux. Okay, so further we want to calculate another case, say case problem 3 or case 3. Last year we did it for 2 cases. So, find out A inside and outside solenoid. Inside and outside solenoid, I want to find out A. So, what happened in the solenoid? Because this problem we already, so this is the solenoid. So, suppose I have a cylindrical system, and over that we have the wires, and this is say axis. Let me draw the axis first. And okay, maybe I can use different color. This is our solenoid. Okay. So, inside the solenoid and outside the solenoid, we need to calculate the magnetic vector potential. So, B inside the solenoid, B inside, the value of B is simply mu 0 Ni. We calculated this earlier, right? And also we have, so we just learned one thing, that integral A dot dl is equal to integration of B dot ds, right, the flux. So, if I have, so this is the cross section, let us make a cross section. of the solenoid, and so this is the radius of the solenoid r, and we have a section inside the solenoid with small r. So, small r is less than r. So, A dot dl if I calculate, because B is perpendicular to this plane. So, A is circulating this line, whatever the line we are having. So, I can calculate this quantity A dot dl. So, A dot dl for this case is simply A, and it is 2 pi r. That quantity again should be equal to the flux phi b, right. So, this thing is nothing but the magnetic flux, and magnetic flux here B dot ds, B is uniform here. So, that quantity I should write B. Magnetic flux here is simply B, which is mu 0 Ni, which is uniform inside this, multiplied by the area, which is pi of r square. So, from here I can find out the value of A very easily. The value of A is simply half of mu 0 N I and then r. That is the value of the magnetic field, magnetic vector potential. What about the outside case, because this is inside and this is the cross section, again this is the cross section we are having. So, let us draw the cross section of the solenoid. This is the cross section of the solenoid, and we have from here to here we have r, and again we have a circular path where we have the value of A, and that now is my r. In this case r is greater than r. Now, again we are going to calculate this quantity A dot dl. That value is simply A 2 pi r, and phi b here, this quantity is equal to phi b, magnetic flux. Phi b here, the amount of magnetic field mu 0 Ni, which is only in this region, not outside, multiplied by the area, but the area is pi r square, because outside that the magnetic field is not there. So, only the area here we need to consider is the region which is shaded. This is the region where we have the magnetic field. This is the region where we should have only the magnetic field, because outside there is no magnetic field. So, the area will be this one. And now, if I calculate A out of that, so my A then 2 pi r is mu 0 Ni then pi r square. So, A from here I can calculate. So, pi will going to cancel out, and it should be simply half of mu 0 in I then r square divided by r. So, you can see that outside the magnetic field is 0, but the value of magnetic vector potential is non-zero. So, if I plot these things, how the magnetic field, magnetic vector potential is changing with respect to r, then we have something like this, which is So, it is linearly changing and then changing at 1 by r. So, this is when r equal to r and r is this side, and I am plotting magnetic potential, vector potential as a function of r. This is the way the magnetic vector potential will going to change inside the solenoid. Okay, so now we will do another important thing, and that is the monopole expansion of vector potential. So, for for a charge distribution for static electricity, for the charge distribution we calculated potential, and we find that the potential can be written in terms of so for electrostatics. So, let me quickly remind what we did in electrostatics. So, in electrostatics what we did, we had a charge distribution, and if I want to find out what is the, so this charge, so this is placed in a coordinate system, some coordinate system like this, and for a small section here, I want to find out what was the value of the potential here, what is phi, which is a function of r, and this is from here to here we had r prime, and from here to here we had r vector, this is curl, this was curly r. But the point is, when we calculated this, we find that this is a contribution of the monopole, it is a contribution of the electric dipole, it is a contribution and so on, it is a contribution of the monopole, dipole, then quadrupole and so on. So, the vector potential I can and the scalar, this is a scalar potential for electrostatic field, can be expanded in this way. So, that was the multiple expansion we had. So, that is the outcome that we figure out. The similar thing we had here. So, here what we do is multiple expansion of vector potential AR. So, previously we did it for electrostatic, and that is the multiple expansion of scalar potential, scalar electrostatic potential, and we find that the contribution is a summation of monopole, dipole, quadrupole. Here we will do the similar thing and see that what happens. So, let me again draw. So, in this case there was a charge distribution, but here we will have a current loop. So, let me draw the coordinate system first. So, this is my coordinate system, and I have a current loop like this. This is my current loop, and the current is flowing here is I. So, suppose the current that is flowing through this is I, and this is the origin, and I want to find out what is the magnetic field produced at some point here, which is, say, okay, let me draw this here at point P, what is the amount of magnetic field produces. So, I can have a section here, say dl prime, and from here to here this is, say, r prime, this is the vector r prime, and this vector from here to here is my curly r, this is r vector curly r, which is r minus r prime. So, this is the geometry we are having. Fine. So, my A is simply at r, we know the expression, and that is mu 0 I divided by 4 pi, and then it is a closed line. So, I should have a closed line integral d l prime divided by r minus r prime. This expression we already defined, that when the line current is there, how the magnetic field can be, magnetic vector potential can be represented. So, that is the, so again, like in the previous case, I need to expand 1 by r minus r prime, and we did it earlier. So, if this angle is theta, then this quantity we did it in the earlier case. So, we are not going to do it here, is summation of n goes to 0 to infinity r prime to the power n divided by r to the power n plus 1, and then p n cos theta. That was the expressor. Okay, maybe I can put theta prime because this is in everything is prime frame, theta prime, and cos theta prime is simply r prime dot r unit vector, and A I can now write as, so what is my A finally? So, A vector field, vector potential is equal to mu 0 I divided by 4 pi integral r prime n divided by r to the power n plus 1, and then p n cos theta prime and d l prime. That is the expression we have. Now, what we do, we just expand. Okay, one summation sign I am missing. So, it should be over sum over n from 0 to infinity. Okay, so now what we do, that we will going to expand this, we will just expand for different n values, and if you do, then I get the first term like mu 0 I divided by 4 pi. For n equal to 0, my first term will be 1 by r, because I can take it outside the integral, and integral 0 dl prime plus second term mu 0 I divided by 4 pi, and then 1 by r square integral r prime cos theta prime dl prime and so on. Now, I can write this term in this way. I can write the first term as a monopole plus a dipole plus so on. Now, let us find one by one what is the meaning of monopole. So, a monopole, this is the monopole contribution of the potential that is contributed due to the monopole here, but we know that there is, for magnetic field there is no magnetic monopole. So, and also the expression is suggesting that we have mu 0 I divided by say 4 pi r and integration of dl prime, and this is a closed line integral of dl, and we know that this value has to be 0. This is 0 because this quantity should be 0. So, magnetic monopole is not there at all. So, that means that contribution should not be reflected in calculating the vector potential of A. What about the dipole? The next important term is dipole. So, A dipole term is simply mu 0 I divided by 4 pi r square, and then we have r prime cos theta prime and dl prime. This I can simplify mu 0 I divided by 4 pi r square and then r dot r vector prime dl prime. R dot r vector prime take care of this r prime cos theta prime. So, I just replace this in this way. Now, I will going to use one identity, and that is integration, closed line integration of r dot r prime dl prime is equal to minus of r cross integration of d a prime, where d a prime is half so this is area. So, this I mean I just write it, but I did not prove. So, I will going to prove that maybe in the next class. This is a lengthy proof, to be very honest, and it is not very trivial. So, we will going to do in the next class, because today I do not have that much of time. But if I consider for the time being that okay, this is the way I can represent r dot r dl, that minus r cross dl, and this is the area, then my magnetic dipole potential term, contribution of that thing, becomes mu 0 divided by 4 pi m cross r unit vector divided by r square, where my m, which we call the magnetic dipole moment, very important term, is simply current into area, or this into area. So, this is called the magnetic dipole moment. So, I mean, this is the way magnetic dipole moment is defined. So, electrostatic dipole moment, if you remember that that was defined like P is equal, I am just writing in the this side, that was charge multiplied by the distance. That was the way, and it is also defined in the integral form like r prime and then r prime rho r prime dv. That is the way also it was defined, but it was charge multiplied by the distance, but here it is current multiplied by the area. In electrostatic, charge is there, and in magnetostatic, current is there, because electrostatic give rise to, I mean, the static charge give rise to electrostatic, and the static the steady current gives rise to the magnetic field. So, that is why Q is here, we have I, their distance is there. So, Q into distance, here we have area. So, these you need to at least appreciate that how the magnetic dipole and electric dipoles are defined. So, in the next class we will going to discuss more about this proof, because I am exploiting one identity here, this one, but without any proof. So, last class we will going to, in the next class we will going to prove that, which will be a little bit lengthy proof. So, we will going to do this proof in the next class to understand how this area are there in the picture. So, with that note, I like to conclude here. Thank you very much for your attention, and see you in the next class.